processor, and today we're going to talk about pass-fail testing. In other words, how can we take vibration data, and we're going to look at vibration data here in a minute, and use that as a way of determining the health of a machine, or it could be any type of a monitored process where we're using vibration. We're also expanding the use of Emiscope for acoustics and vibration. So any signal that we typically can acquire with a FFT analyzer or a data acquisition system. In this case, you can see down here on the screen the use of a battery-powered portable analyzer. Now, these are very popular in-process plants throughout the world. Again, the 80-20 rule, 80% of the vibration data that's acquired on machinery is done with these portable devices, battery-powered, class 1, so they don't cause fires and so forth like in a gasoline refinery, that sort of a thing, or a chemical plant. But Emiscope, Vibrant is a software business. Emiscope is a post-processing software package that can take vibration and do lots of different things with it. So we're going to show that today. The other piece of the center here is automated Emiscope post-processing. So we're going to demonstrate that. And we use what we call hotkeys now in Emiscope, a standard part of Emiscope. When I press a hotkey, it executes what we call a script. And a script is merely a spreadsheet of Emiscope commands that Emiscope executes from top to bottom. And we'll see how those work here in a minute. And then up at the top of the diagram is something we call our console software. Now, this software is not licensed. Only Emiscope is licensed. So once you own one of these MSS packages, you can install console on as many computers as you like. And you can see here in the picture we've got it installed on a touchpad, or on some computers in an office, or even on a smartphone. So these are applications where we can look at the data. The console is basically a graphics package similar to Emiscope, but it doesn't have the processing power that Emiscope has in it. It's more of a graphics package for looking at trend plots, looking at a waterfall of your spectra, and we have an option to it called Fax. Now, Fax stands for Fault Correlation Tools. And I'm going to demonstrate that here in a minute, where we can use Fax as a pass-fail indicator, very simple indicator, where we can take a shape table. You're all familiar with shape tables in Emiscope. An ODS or a mode shape that would be saved in a shape table. And we can compare the data in that shape table with data that's stored in an archival database. So if we ever see a set of shape parameters that matches anything in the database, then we recognize that as in this case, we're going to call it a pass-fail condition. So if Fax recognizes the same shape data that we've identified with a pass condition, then it will indicate with a bar with a value of 1 that is valid data. And if the data changes significantly, then the Fax bars will drop to 0. So I'm already giving you a slight indication here of what Fax uses. It's like the modal assurance criterion, or the MAC metric. Now, that was developed many years ago for comparing two mode shapes. A MAC value of 1 means that two mode shapes are the same. More specifically, they're collinear with one another. A MAC value of 0 means they're quite different. Fax uses something that we've created at Vibrant for use in MeScope. It's a standard part of MeScope called a shape difference indicator. And it works very much like Mac. A value of 1 means that two shapes are identical, and a value of 0 means that they are numerically different. Now the difference between SDI and Mac is that Mac actually takes the difference between the two shape vectors, and so it's computing a difference, whereas Mac is simply telling us whether the two shapes are lying on the same line or collinear with one another. Not quite as accurate for working with machine data, ODS data, and we'll see here in a minute that we're actually going to just use some modal frequencies and compare them with data that's stored in the database and use that as a pass-fail indicator, the modal frequencies of our old friend the Jim beam. So let me close this, and now we're looking at MeScope, and this is a project. Up here in the ribbon you can see some hotkeys. These are hotkeys that I created in MeScope. They're part of this project. We'll come back to them in a minute. Let me just show you some pictures of how we took this experimental data. Very simple process. I'm going to open some of these added files. So here are some pictures of the Jim beam, and this is a very simple test. We also have an option to our monitoring software now called QTS, or qualification testing. We're going to use the MSS, the machine surveillance series, but functionally it's going to do the same thing. So you could think of it either way. I've got something in production, or I've got a machine out in the field and I just hit it with a hammer, and I have a triaxial accelerometer measuring response. So that's all the data that we're taking. In this case, it doesn't matter where I hit it, where I measure the response, because I'm going to use modal frequencies to indicate changes in the torque value of one of these cap screws over here. So you can see there's a cap screw here, and it's going to be tightened with varying amounts of torque. And we'll see that the modes of this Jim beam, which is just 3 plates attached together with cap screws, will change in frequency as I tighten the cap screw with a torque wrench. So this little wrench over here, I can set in a number of inch-pounds of torque using the English units, and then just hit Jim beam anywhere on the Jim beam with a hammer and measure its acceleration anywhere on the Jim beam. Now I want to put the accelerometer where I'll get some what we call an anti-node of a resonance, so we get some nice peaks in the data, but we'll look at some of this data here in a minute. Now an FRF, we're going to look at FRFs first, where the hammer actually measures the force input, it's an impulse, and measures the response due to that impulse. So we'll look at FRF data, we'll curve fit that, we'll use the modal frequencies of 6 of the modes as an indicator of a pass-fail of the torque of this one cap screw here. And we'll see that Fax can identify exactly the amount of torque that's been applied because we've saved the frequencies for each of the cases of torque applied to the cap screw. Then we're going to do the same thing with just the accelerometer data. Not the hammer, just the accelerometer, and we'll compute cross spectra between one of the channels. That's a triaxial, so I get 3 acceleration measurements there. I'll use one of them as a reference, and so that spectrum will actually be an auto spectrum of that channel, and then a cross spectrum between that acceleration and the other 2 channels. We'll curve fit some of that data, and again, if we can't measure the force, we just measure the response. We can curve fit that data and compare modal frequencies again. And then in the third case, we're gonna do away with the curve fitting altogether and simply compare spectra over a frequency band. And we'll use the same frequency bands that we use to curve fit the data. And there we're simply going to use the fax calculation to tell the difference in spectra, a good one versus a reference or a baseline, and measure, again, with numbers between 0 and 1, the difference between a spectrum that I measured and one that I've already put in the database as a good spectrum. So that's the idea. Let me walk you through some more pictures here, and then we'll move on to Emiscope. So here's another picture. You can acquire this data with as few as 4 channels, 1 channel for the force input and then 3 for the triaxial accelerometer. As I said, in the second case, we don't even care about the force measuring the force. That's only for FRFs. If we're simply looking at cross spectrum or auto spectrum, then we could do it with as little as 2 channels or even a single channel if we're just doing the auto spectrum only. So we're going to look at basically using vibration data in 3 different ways here today. Okay, so only modal, this is saying that it doesn't matter where I hit it and where I measure the response for pass-fail testing. I simply want to make sure that the modal frequencies that I'm curve fitting and putting into the database are going to be, I can get them from these measurements. So on a Jim beam like this, a simple structure like this, I'd have to be very unlucky to mount the accelerometer in a place and then hit with a hammer so that I get no vibration at all. So that's the only assumption, that the structure will vibrate when I impact it. Okay, we could do this with torques on all 3 of these, or thinking about a production environment where I need to assemble things properly. I could have a lot of different physical properties that I'm interested in ensuring so that I have a good assembly. In this case, we've simply tightened the cap screw, this one cap screw, using 6 different amounts of torque, and they only vary by 5 inch-pounds, which is not very much, but we'll see in a minute that that's enough to measure and distinguish each of these cases by looking at the modal frequencies. So anyway, there's the pictures of our experimental setup. Now, as I showed in the first diagram, we've already collected the data, and that's a similar situation to any walk-around data collector, where we've already collected the data. In this case, we've got it stored in a data block. Now, if I was processing walk-around data collector data, I would set up Emiscope to automatically open up a file on the disk and read in the data. Now here we've got time records, so we're using, let me make this large here and we'll just take a quick look at this data. So I've got all 6 cases in here. There's 24 measurements, and each group of 4, I'm displaying the top as the impulse from the hammer. These 3 are the responses of the accelerometer, the triaxial accelerometer. So as I scroll down here, I've got each of the cases of experimental data that I've collected by impacting the Jim beam with different amounts of torque. And I think they might be labeled over here. No, they're probably not. Oh, yes, they are, right here in the label column. So let me make this a little bit larger so you can see. See, the first 4 are the 10 inch-pounds. The next ones, 15, are the next 4 are 15, and so forth. The other thing to notice here is something that we use in Emiscope called the measurement set. And we add that to the DOFs of these measurements. So here you can see 99Z. What that means is I don't care where 0.99 is. It's just going to be anywhere that I impacted this structure. And here is point 1, X, Y, and Z. That's where I've located my accelerometer. Again, that can be anywhere. And that is measurement set 1. In other words, this data was simultaneously acquired by the analyzer when I impacted the Jim beam. So we call that measurement set 1. Here's measurement set 2, 3, and so on, all the way down to the bottom where we've got measurement set 6. So 6 experiments that were done by impacting the Jim beam with different torque values on the cap screw. So that's the data that we've imported in Emiscope. Now we're going to post-process that data with our acquisition window in Emiscope. And this is showing, and this is set up with the 6 measurement sets. This is where we define a measurement set in acquisition because we want to post-process data from the same measurement set. So I can press a key here on my keyboard and walk the acquisition window I've set up. You can see this is measurement set number 2 of 6. As I press the key, there's number 3. The acquisition window is showing me the data out of the data block on the top. Those are the time records. On the bottom is the FRFs, the 3 FRFs that are being computed from these time records. So as I walk through here, there's number 6, and then it, okay, so it's walking in reverse. Let me go forward. There's number 1, the 10 inch-pound case, number 2, number 3, number 4, number 5, number 6. So Emiscope has been set up to automatically acquire the data out of the data block as a post-processor, compute FRFs. Now here you can see that I've set up the FRF as my computed function. You can see them down on the bottom here. There's 3 of them. This is the auto spectrum, or the log magnitude of the FRF. I can change this and display Bode plot. So there's the FRF for the Z direction. There it is for X, Y, Z. Okay, so that's the second step. That's all automated here in Emiscope. The third step is that we're going to take these FRFs one at a time and we're going to curve fit them. So here's the curve fitting, and this is all automated in Emiscope, so that when I press a hotkey, it's going to automatically curve fit the data, and you can see here that it's already done it with the red line, the curve fit function laying on these particular 3 FRFs. And then finally, over here, this fourth is a shape table, and here's the data that's being stored. 6 frequencies for 6 modes, and then down here is the mode shapes for just the 3 responses, X, Y, and Z, but we're not interested in those. We're only interested in the frequencies. So let me start this, and you can see my hotkeys up here. My first one's a reset. That just simply lays things out. And now if I press the 10 inch-pounds case, that's measurement set number 1. And okay, so it rattled through the curve fit. That was very fast. Let me slow this down a little bit. There's a way to tell the scripting, don't go so fast here. You put a delay in. So I'm going to open up this script here. This is the one that does the curve fitting. And you can see that I'm doing a quick fit. This is setting up a band, display the cursor in a band, do a quick fit, display the cursor in a different band, do another quick fit, followed by another one. This is very simple use of Emiscope, using the quick fit. And so there, and then we got some other commands in here. So let me just go back and run this first case, the 10 inch-pound case. So it's going to pull up the data, and now you can see it's curve fitting in those bands, and there it's synthesized the complete magnitude and phase, but the end result here is that we've got some modal frequencies and some damping. So if you watch over here very closely, let me zoom this in a little bit, and watch these frequencies change as I acquire the data for the different cases. So here's the 15 inch-pounds case. And the easiest way to see the difference is to watch down here. Well, it still says 565. Let me just go to my options box, and under numbers, I'm going to give it one more significant digit. So if you watch over here, the 564.6, now I'm going to try 25 inch-pounds or 20 inch-pounds. So it's now curve fitting that data. And you can see 565.7. So the frequencies are going up as I apply more torque, which is something that we know from modal analysis, well known that resonances are a function of the physical properties of the structure. So as I increase the stiffness between the top plate and the back plate, the frequencies increase ever so slightly. But we'll see in a minute here that Fax is a very accurate way of distinguishing each of these cases of modal frequency. And once I've identified them in my database, each of these sets of frequencies, then if I ever see them again, I can say, well, that's what I was looking for. Now I'm going to turn on the archive data, so I'm going to press this button, and that will connect Emiscope up to the archival database. And now we're all connected, and now I want to come over here and open up the console, which is my graphics tool for looking at data that's been archived into the database. And so here it is. Let's go back and go to the machine gallery. Now this database is specially designed so that you can see I've got a lot of machines in here, but this one down here is the one that's now connected and live in the database. It says the machine is on, the project is open, and this is a project called Jim Beam PassFail with FRFs. So if I click on this, double click on this one. All right, well, let's go back and look at some things here. Okay, this is a trend plot. It's not quite set up properly. This is where my data will be trended into the database. Now this is how I control Emiscope. Those same hotkeys that are in Emiscope over here that we were using also show up in console. So this is how I can remotely control what I just did for you in Emiscope from console through the database. So if I press one of these keys here, you'll see Emiscope in the background. Let's just see if I can share the screen with these two. And I'll put Emiscope over here. Okay, so here's Emiscope on the right. Let me just reset everything here so you can see it better. All right, this is going to, now remember I slowed the curve fitting down. Let's go speed the curve fitting back up again so this will run a lot faster. I'm going to go over here to my script, and this is the script that's doing the curve fitting. I'm going to say turn that, don't delay after each quick fit, and let me just set this back. Now each time I reset, I need to reconnect to the database. That's just the way I've coded it, but you can see how fast it's doing this. And over here is one of the modal frequencies. Now if I go here to my let's see, well, I've got it set up here with several different graphics. There's my model of the Jim Beam. There's my trend plot, and we're going to come back to the trend plot. Something called gauges. These are the mode shape values. I'm not really interested in them in this case. Something called an event log. Now what I've done here with the event log is I've identified all of the cases of frequencies. Let me see if I can show you. Well, let's just go on from here. And in this case, I've identified the three cases of torque, 15, 20, and 25, and I've made those active as three cases of frequency that are my pass condition. If I ever have a torque of 10 inch-pounds or one of 30 or 35, those are fail conditions. It's either too loose or it's too tight. And Fax is my indicator, and this is called a Fax Bar. And this, again, as I explained earlier, this is the SDI calculation between frequencies. Now, let me just show you how this Fax Bar has been defined. I'm going to use my event storage for comparison, and I'm simply going to use the 6 modal frequencies that are being curve fit over here and logged into the database from the shape table, and I'm going to compare those with what's already stored in the database. See, I don't want to use the mode shape data. That's this data down here. I'm just going to use the event storage. So let's close that. And let's just try this out. I'll close this, and now I'm going to come up here and hit a hotkey. So I'll hit 10 inch-pounds first. All right, Emiscope did its thing, and it said the Fax Bar is the closest thing to it was 15 inch-pounds, but the value is 0.4. That's a failure. Now let me go and try 15 inch-pounds. The Fax Bar jumped up to 1. It says that one matched with one of my events that I've logged into the event table here, and that was this one right here. So it said, I recognize that as 15 inch-pounds. That's a pass. Let's go back to Fax. Let me try 20. Okay, Emiscope did the acquisition, did the curve fitting, and here's 20. So again, I get a Fax Bar equal to 1, and this next Fax Bar over here is saying 25 is pretty close, 77%, but the frequencies that I just acquired from the 20 inch-pounds case are a pass. Now 25, let's see what 25 looks like. There it is, 25 again, and the next closest one was 15 at 0.5. Not a very good match. However, it identified that. Let's go to 30. Now remember, 30 was a case that was a failure. I don't want to accept that, and the Fax Bar dropped way down. And let's try 35. There's 35. The closest one to that was 15, and that's 44%. That's a failure. Go back here and press 15. Emiscope is running under remote control, and bingo, I have a pass condition. So that is a demonstration of pass-fail using FRF data. Now let's go open a different project over here. I'm going to close this project in Emiscope. So let's close the project. Do I want to save it? No. And I'm going to open another project here, and it's called PassFail using XPSs, or cross power spectra. Okay, I'm going to put I'll put console down here for a minute, And let's make Emiscope real big. And I'm going to go to my hotkeys and reset everything so we can look at what's on it. Okay, this looks very similar, except what we've done now, this is the same data, but in the acquisition window, let me open this up here, and we'll see that now I've turned off the first channel, which is the force channel. And on the second channel, the second, third, and fourth are the accelerometer signals. Remember, they're up here on the top. Here they are up here. Since I've turned off force, all I can look at in the top now are the accelerometer, the responses. And the first one I've said, this is, rather than an output, it's going to be both an input and an output. So we use this terminology as the reference rather than an input here. I could just say that 1x accelerometer is an input, but I'm going to say it's both input and output. So what that's going to do is compute, up here you can see a cross spectrum between channel 1 and itself. Well, that's an auto spectrum. So what we have down here, you can see is just an auto spectrum. There's the magnitude, the phase is 0. That's what we would get from a single channel analyzer. The second is a cross spectrum. We're computing cross spectra here. So if I scroll down, there's the cross spectrum, magnitude and phase. So the phase is with respect to what? With respect to 1x. It's a cross spectrum between the channel 1x and channel 1y. And then the third one is another cross spectrum. This is the one between 1z and 1x. So acquisition window is now going to post-process the same data, but now we're going to assume that we didn't measure the force. This could be a running machine. This could be something we hit with a hammer, but we don't actually measure the force. We're simply going to curve fit the 3 cross spectra. Well, the first one being an auto spectrum, second one and third one being cross spectra. And then we're going to put the frequency and damping in this shape table here, just like we did with the FRF. So we can curve fit in Emiscope. This is called our OMA option, our operating model analysis option. So let me just push one of these buttons here and we'll see what happens. Same thing. This is the case of now the curve fitting is going on here with a delay, and this data has been processed. Yeah, you can see it looks a little different in the acquisition window than it looks over here in the data block window where the curve fitting took place. That's because we applied what we call a deconvolution window to the cross-spectrum data in order to make it look like an FRF so we can use an FRF curve fitter on it. And that's what has shown up here. So it's a windowing operation that we do in Emiscope with our OMA option so that we can curve fit operating data. Now let me just run through these buttons here and you'll see it's going to acquire different data, and it's curve fitting with the quick fit, and then when it's done it's resynthesizing the fit function, the red line, and laying it on top of the actual data. Now you can see that window that we applied to the data between acquisition and curve fitting got rid of a lot of the noise. That's a part of the process of the deconvolution window, and then it also added phase to our auto spectrum up here so that the FRF curve fitter worked properly. Let's do another one. Here, I'm going to try the 25. Now the curve fitter is delaying after each curve fit, so let's get rid of that delay. I'm going to go back in here and do the same thing I did before. I'm going to open up the script. I'll make this large so you can see it better. And I'm holding down the shift key to or the control key, sorry, to expand the spreadsheet. So this is a script window with the curve fitting commands in it. You can see that it's got the data block, and here we just called it 3 FRFs. I didn't change the title, but that's this data block right here. And those are not FRFs, those are the cross spectra, but that's okay. I'm going to turn off this delay, and let me set the window back, and I can press any one of these, and now we'll see it very quickly rattle through curve fitting this data. Now I'm going to attach it to the archival database, and now Emiscope is archiving that data in the database. Let's get the console up here and look at it. So let's see, we got console there, we got Emiscope here, and now I need to go back to my machine gallery, and you can see that I've got this project now open in the database. It says it's open, the machine is on, so it's Emiscope has logged some data in. That's what that means. The console says, oh, I got some fresh data from Emiscope. So I'm going to double click on this, and here's what it looks like. We might have a little setup work to do here. Here are the data that's coming in, the frequency damping and the 3 accelerometer from the curve fitting, the limited mode shape, if you will. Now I need to set this up. This is not set up quite right. So let's just, let me maximize this here for a second. Well, oh, come on. Okay. I'm going to go, this is a, and I'm going to go back here and turn on, okay, I've got gauges, I've got a trend plot here. This trend plot has got 1 data point in it. Let me add a few more data points. I'll just go and see what happens here. Okay, so now I got 2 data points, and I need to set this up. Let me go and display the plot selection, and I just want to look at the highest frequency. So let me see what it's plotting in here. Well, it's actually plotting the mode shape data, so I don't really want that. Okay, now I've got nothing there. I'm going to go down here and just tell it on the mode number 6, show me the frequency. And we'll just look at that, and now I want to also change my charting over so it's a little easier to see. There it is, a bar chart. So let's just run this thing for a little while here and see what happens. Okay, there's the 10 okay, I didn't see anything happen over here, but let's see if it knows what to do here. I'm going to set this up so we can see everything happening here. I'm going to reconnect. Okay, so you can see the data coming in down here. Let's go to 15. Okay, so you can see that frequency jumped up there. If I put the cursor on, I'm just looking at the highest frequency. Let me put a few more of them in here and we'll look at them. You can see that frequency climbing as we look at data, post-process data for the increased torque values. So there's all the cases. I've put them all in there. So let's go back now and look at our whether we've set up the event log properly. Okay, so I do have an event log here where I've identified those cases already, but I'm going to say turn off, again, like we did before. Let me see if I can make this a little larger. Okay, you can see it better now. So we're going to say that the only cases we're interested in as a pass condition are 15, 20, 25. Well, let's take out 15. So only 20 and 25 this time. Now let me go and look at my fax bars and see if I have them set up properly. Let's go into this definition here of the fax bar. Okay, it's going to use the event storage. It's going to use all 6 frequencies. That's correct. And you can see that I've only got 2 of them here, and they're very low. So whatever my last data was, which was 35 inch-pounds, it's a fail condition. So let me go back and try 10 inch-pounds. Okay, Emyscope's shoving the new frequencies into the database, and it updated, and it's still a fail condition. 15 was a fail condition. Let's see if that comes up. Still a failed condition. All right, let's try 20. There it is. I have a pass condition, 20 inch-pounds. Let's try 25. There it is, another pass condition. Let's try 30. Failed condition. So the other way to know when Emyscope is done, because it's running under the hood, I really can't tell if it's remote or I'm just looking at this on an iPhone or an iPad or a tablet like that. So I have an indication here. Now, Emyscope's also telling me what it shoved into the database here. I can have little messages come from Emyscope to the machine telling it that I just archived some cross-spectrum data and number 3 case. Okay, we're kind of running out of time here, so I want to show you the 3rd case, which is we don't need curve fitting. We can simply use the data itself. So let's go back here and make this large. And I'm going to close this project, and we'll open a 3rd project. No, we're not going to save it. And this 3rd one is just called using Spectra. So pass-fail condition using Spectra. Now it's very similar, except we're not going to do curve fitting this time. We're going to actually use the same bands, but we could set this up to use any band of data or all the data. And we're going to use a special command in Emyscope which calculates the difference between the data that I'm looking at here. Let's go back to the hotkeys. And you can see I've got a number of hotkeys here, but I've got an extra one called new baseline. So what that's going to take is my current set of spectrum data and say that is the baseline. And then Emyscope will calculate the difference between the spectrum and the current one. So let me just run through this a little bit here and you'll see what happens. I'm going to go with the 10 inch-pound case again. Now what it's put over here is not modal frequencies, but it's put SDI values. Here, let's just look at this command actually puts MAC and SDI values. So it creates a shape table when it compares the 2 bands of frequency. And here we've got 6 bands of frequency, and so the first 3 would be the first band, second band, third band, fourth band of frequency. I could just use one band. Here we've used the same bands as the curve fitters, and you can see the values are all rather small. These values of MAC and SDI are always going to be between 0 and 1. You can see the label here that says what I'm looking at is not a ODS or a mode shape. I'm looking at MAC and SDI values. This is a standard feature in MeScope. Then what the scripting does is, we're not interested in MAC. We simply save the SDI values, select that shape, and put them into a different shape table, and this is the one that gets archived into the database. So let me go back and run this a couple more times for you so you can see. I'll try 15. Now, I don't know what my baseline is, but I'll soon find out, because it will, these SDI values will all turn into 1, because that will say, bingo, see, they're all 1 now, because this set of data is identical to my baseline set of data, and that was the one that I picked by pressing this hotkey. So if I go on and press any other hotkey, you can see the values drop down, although the 90% here, this is fairly close. This set of data is fairly close in frequency and in waveform to my baseline, which I set here as 20. So what I can do there, again, now we're just logging SDI values into the database from MeScope. So let me go ahead and activate it, or let's say now it's archiving, and we'll go back to console here. Now I'm gonna close this guy. Well, let's close this whole. These are okay. I'm back to my. Here you can see this the Spectra now. This was the last one I had open, but here's Spectra now. This machine is open, and because I connected to the database. So let me go in here. Now I've got some different bars here. We'll just clean this up a little bit so we can look at the same thing. I'm going to go to my trend plot. Okay, here's some different colors, but this is trending the one of the values out of my MeScope over here. Let's just see if we can get this back here. And, okay, let me reset it so you can see everything, and then we'll reconnect. There it is. It's just grabbing data in various bands, and so you can see these values now, instead of being frequencies, they're SDI values between 1 and 0. So if I go and press 10 inch-pounds, very low SDI value. So let me just walk here and we'll look at the SDI values of each of these. So that one's very low. This is our baseline data that should pop right up to 1. There it is. Okay, let's go past the baseline. Now remember, we're storing in 18 different SDI values, and so Fax is simply going to look at those values and say, does this pattern look anything like the cases that I have stored in the database? And that's what we'll do with Fax here. You can see these are jumping around. So we can go in, let me do the 25 inch-pounds. You can see that it, for this particular component, is a value of 0.9. So that's, anything above 9 is a very similar, what it's indicating is that the spectrum is very similar for this particular component. we can go look at that and see what it is real quickly. Let me go into the display and see what I'm actually displaying here. Okay, it's displaying the SDI value for just one component of the shape, all the way down here at the bottom. Remember, there are 6 times 3, 18 components. Now let's go over and look at Fax and see what it's doing here. Now I've got a Fax bar called torque event log. I've got a bunch of cases in here, so I want to go back and look at my event log. And let's just say that we only want to use the 20 and 25 as a pass condition. Everything else is going to be a failure. And let's go back to Fax, and let me see what Fax is actually going to use out of the database. Okay, it's going to use all of the SDI values for the 6 bands. And remember, there's 3 measurements, so 6 times 3, there's 18 values here that it's going to match up out of the database. So let me, okay, so there's a case where it's 25 inch-pounds matched up, and the second case there is 20. Let me go push 10 inch-pounds and see what, bingo, see there's a failure. 10 inch-pounds, Emiscope did the processing, the Fax bar dropped way down to 50%, and it's not matching up well with anything. There's 15 inch-pounds. Bingo. A little better, but 76, it's still not matching up. Now let's go to 20. Oh, there it is. 100%, there's 20 inch-pounds, and 25 is close by, 95%. So it found those in the database. Let's go. So Fax will look for the 10 best if it can find them. Now here I'm telling it just look for anything that matches up with 20 or 25 inch-pounds out of the database. But if I simply want to compare the current data with up to 10 other that match the closest in my database, I can use it that way also. Let's go to the 30 inch-pounds. And bingo. Now 30 inch-pounds drop down to 94. That's pretty close. Let me show you one other thing. I can change the sensitivity of Fax, and this is something unique with this metric. So I'm going to go in here, and you can see that this sensitivity is set at 4. Let's crank it way up. I'm going to crank it up to 10. Now, I don't have time to explain all this detail to you, but see what it did? It pushed the bar way down because it made the SDI much more sensitive to the data in the shape table. There it is. See, it said, hey, that's 20 inch-pounds, no question about it. Let's look at this one. There's 25 inch-pounds. Now I go over here to 30. It failed. 30 inch-pounds was 2. It was a failure condition. 35, even bigger failure. Let's go down here to 1 inch-pound or 10 inch-pounds, the first case. Failure. So this is a kind of a thumb wheel I can use in Fax to make it more sensitive to the difference between the data stored in the database and the current data coming in from Emiscope. All right, I think, Mark, that concludes my presentation. Do we have any questions?
We don't have any questions at this time. If you do have some questions, feel free to email them. Easiest email is probably just at sales@vibetech.com. and we will get those questions answered for you. We did record this webinar, so we'll get this posted out to the YouTube channel, which you can find by just going to YouTube and typing in Vibrant Technology. We have all of our past webinars as well, and we'll probably have this one up here in about a week or so. So if there's something that you missed or you want to go back and review, you'll have a copy of the entire webinar up at the YouTube page.
One more thing to add, if you own Emiscope, and some of this capability is in the advanced options of Emiscope. The SDI, all the scripting and hotkeys is available in any package of Emiscope, but some of the post-processing that we're doing here is more advanced ones. Now, if we can send you these VTPRJs, all the information both for running fax and running the scripting and the hotkeys between console and Emiscope is all contained in the VTPRJ, the Emiscope project. So you can run these if you want to pursue the use of this capability further. Just send us an email and we can get you set up with the software, and we can certainly give you a trial license that will allow you to do all the things you saw here today. So thank you for coming, and we'll look forward to having you back here in January for another webinar.